Arizona State University and Science are recognizing researchers who address pressing problems. The ASU Science Prize for Transformational Impact honors early career scientists developing innovative solutions to today's biggest challenges. Hear from the inaugural winners on ASU's Lab Coat Optional podcast and visit science.org/ASU to apply. This podcast is supported by the Icahn School of Medicine at Mount Sinai, an international leader in research, education, and patient care. The medical and graduate school is part of the Mount Sinai Health System, one of the largest academic medical systems in New York City. Ranked among the top recipients of NIH funding, researchers at Mount Sinai have made breakthrough discoveries advancing the health of patients. Here, clinicians and scientists push the boundaries in cardiology, cancer, immunology, neuroscience, genomics, geriatrics, environmental medicine, and artificial intelligence. The Icahn School of Medicine at Mount Sinai, we find a way. This is the Science Podcast for June 25th, 2026. I'm Sarah Crespi. First this week, a roundup of science policy changes from the last month to U.S. science funding and practice with ScienceInsider editor Jocelyn Kaiser. After that, we have senior editor for Science, Michael Funk. He talks about a trio of papers publishing this week that finally have cracked the structure of the proteins behind color vision. Finally, the latest in our science biography series. Book's host Angela Saini interviews science writer Georgina Ferry about her groundbreaking book on Nobel Prize-winning crystallographer Dorothy Hodgkin. Our policy reporting team has been very busy, probably for the past year and some months. They're constantly following developments in the U.S. science agencies and the effects policy changes have on scientists' work and their lives. This week, Science Insider editor Jocelyn Kaiser is here with some important stories from the last month. Hi, Jocelyn. Thanks for coming back.
Hey, good to be here.
So the first story we're going to talk about is something that time-wise happened at the end of May, and it's still making a lot of waves today. The White House is basically trying to increase the amount of political oversight for grants that go out to scientists, and this is a proposal out of the Office of Management and Budget. What are some of the big changes being proposed here? This is not approved yet, but this is something that has been shared around and is out there for comment.
This proposal, which would affect all grants, not just research grants, would change how grants are now awarded and the control over who these grants go to entirely in the hands of political appointees. And right now, the biggest factor in deciding where a grant goes is really the peer review, the outside scientists who review the grant. But this new rule would make those reviews only advisory to the political appointee running the agency or maybe higher up in that department. And this has really got researchers very, very worried that political considerations are going to control where funding goes and not the best science.
So there are all these committees that evaluate proposals and then they rank them, and then some of them end up with funding based on those conversations of experts. Instead, there's another step going to be added on top.
That's right.
I think in the story it mentions that there's actually 400 plus pages in this proposal. Is this kind of the big change that everyone is most concerned with?
Yeah, that is the big one. There's a lot of other stuff in there. The proposed rule would also make it easier to terminate grants. Last year, the Trump administration canceled thousands of grants that touched on diversity, equity, and inclusion, and other topics like climate change. And this would make it easier for the administration to not fund those studies at all. There's also stuff in there on international collaborations, would make it harder to collaborate with foreign scientists.
What are people saying? There is this comment period. Like, are people pushing back on this?
Many, many scientific organizations are mobilizing to oppose this. They're urging their member scientists out there to file comments. There's a comment period going on till like mid-July. And there have been, I just checked, over 37,000 comments filed at this point, which is a lot of comments for federal rulemaking on any topic. We don't know exactly what those comments say, but most likely most of them are opposing this proposal.
What are they trying to do? Like, what problem are they trying to solve with this proposal?
The OMB, Office of Management and Budget, says its reason for doing this is to increase transparency, accountability, and oversight. The way it worked before is what we talked about a few minutes ago, where the experts reviewed the science, and that's where what was driving the decisions. But this administration feels that, I guess, that's not accountable and transparent. And so that is why they want to put this new process into place.
If you put a political appointee at the top, they're going to change out every time the administration changes. And so, how things are funded, who's working there, who has the inside knowledge, like they're all going to change every time there's any change in politics.
Yeah, and that's one point people have made. This is not necessarily a good idea for Republicans because the next Democratic administration could then impose its priorities and overrule the science.
There is something about publishing, which I was kind of surprised to see. There was kind of this like, okay, well, here's one positive thing. Like, there's nothing in here that says that these costs that are paid to the universities that get grants, that these like housekeeping costs are not written into this law. That's something that's the administration has really tried to push, Congress has pushed, and courts have pushed back against. That's not in here. But there is a change to how publishers are paid out of grants.
Yeah, and so there's some wording in there that says you cannot use grant money to pay these article processing charges or APCs, which are fees that authors pay to have their journal publish their paper in a way that makes it immediately available to read. This rule would bar scientists from using money from their grants to pay those fees. And there is a new federal mandate that if you get funding from the government to publish your research or to do your research, you have to make it immediately available. And so that is going to make it even harder for scientists to fulfill that mandate if they can't use grant money.
Sometimes these processing fees are in the thousands of dollars.
Yeah, and it's a little confusing because one part of the government is saying we want you to make your research immediately available to read, and yet another part of the government is saying we're not going to give you money to do that.
This is like a huge discussion that people have been talking about how the government regulates the publication of research for 40 years, 50 years. And to just put a line in here about it that totally changes it, it just shows you that this document has got a lot that's going to affect science and scientists. Let's go to the next story that you flagged as something that people would kind of rose to the top from the last month of coverage. And this is on the reclassification of employees of the federal government that basically takes them from civil servants that have protected roles to political appointees that can kind of come and go and turn over with the administration. They're easier to fire. Can you talk about this change? And it happened, what, at the beginning of June?
Yeah, so this is another thing that people see as politicizing how science funding is awarded. It would affect something like 8,000 people and in 2,500 positions. A lot of them are at science agencies. They're at the National Institutes of Health. It's a lot of people who are helping run these grant programs. And as staff, it seems to be more the people who help manage the grants, like the numbers side, and some other positions at other agencies seem to be people who maybe manage resources, like at the National Oceanic and Atmospheric Administration. What they're trying to accomplish here is a little bit unclear, but what people are really worried about is that the people in these positions who are now career civil servants will become political appointees and that they will have to be hired at the will of the administration and could easily lose their jobs. They wouldn't have the protections they now have.
So, like, if you make a decision that's politically unpopular, but the evidence all points to it, that's no longer necessarily going to be available to you as an option.
Right.
It is interesting to kind of look at how this plays out because you say, oh, they're changing 2,500 job titles, but how many people have that job is harder to figure out.
Our reporter, Jeffrey Mervis, really tried to figure that out. He talked to people who were at NIH, and it's hundreds of people at NIH, but at the National Science Foundation, it may not be a whole lot of people. So it seems to depend on the agency.
And this is an executive order. So this isn't necessarily something that people can comment on, or it's much more like contained within the executive branch.
What I don't know is if there will be lawsuits filed about it, the way there have been with many of these other actions.
This story caught a lot of people's attention. This is something that happened at the American Diabetes Association meeting. This was first week of June, second week of June. This was definitely made a big splash on social media.
What happened was this was American Diabetes Association meeting in New Orleans, and the NIH director was scheduled to speak at this meeting.
Oh, Jay Bhattacharya.
That's right. Outside the auditorium where he was going to speak, some members of that society were handing out an editorial they had published just a few days before in one of the association's journals, decrying all the things that have happened under Trump to science. And they wanted people who went in to listen to that lecture to be aware of what's happening. And so they're standing out there. These are people who are on have been officers and on boards, and police come up to them, security, I think it's security at the convention center, and they are escorted out of the meeting, told that they are not going back into the meeting. Their lanyards, their name tags are taken.
These are members, these are people who are
Yeah,
part of the society.
the NIH director actually was not the one speaking. He canceled, and instead someone else from NIH spoke. But this is just something that is unheard of to happen at a scientific meeting. And the leadership of the association at first said that they have a prohibition on, I think, any sort of political activity at an event. And I guess they considered that this was political activity.
I mean, they were handing out an editorial that was published in the journal, like the flagship journal of this society.
Yes.
This is strange. It was published in the journal, but you can't like talk about it at your meeting.
Yeah, I mean, it did have a disclaimer on it saying that it was not endorsed by the journal, but still, it was published in the journal. And to treat these scientists in this way as just these experts is just kind of unbelievable. And then a couple days later, the association started to backtrack. And then in the end, their director made this video saying, "We're sorry this happened. It shouldn't have happened, blah, blah, blah." It was pretty clear that it was not NIH asking them to remove these scientists handing out the editorial. It was the leadership of the association. And so, yeah, so now there's a mea culpa from the association, and we'll see what happens next.
The kicker here is basically this would have been a handful of scientists handing out a piece of paper to attendees at a meeting. And instead, it turned into basically an international incident that many, many thousands of people have heard about. All right, the last one we're going to talk about today is a really interesting study that just came out, basically describing kind of the trickle down effects of some of these policies that have been put in place since the Trump administration started.
Researchers got access to NIH data on demographics of the investigators who were funded in fiscal year 2025, which ended in September. They had information on the ethnicity and race of last year's researchers and the fellowships, people who were in training. And there's a pretty stark drop. Well, there was a drop in how many investigators were funded overall. And it's been known that because not as many people were funded, but the drop was bigger for minority scientists, particularly for Black scientists, dropped by 10%, Hispanic dropped by 7%. To me, the really alarming part was this drop in fellowships. I mean, that's a smaller number of people, but Black scientists receiving fellowships dropped by 40%. So it went from 205 to 122. And then Hispanics, which is a bigger number to start with, dropped by 33%.
And this is, if you think about fellowships and training, it's like the pipeline to senior scientists. Like this is an entry point for these people. And once you cut off the funding for them, they're not going to be able to take that next step and become part of the like permanent scientific workforce. So it's a real impact.
It is. And it reflects the fact that last year, NIH, soon after Trump came into office, just pulled down all these funding opportunities aimed at building the workforce, bringing in people from diverse populations.
So this is about NIH funding for PIs and fellowships. But is there any data out there on NSF or other grant agencies, grant making agencies?
I don't know that I've seen data on the diversity of fellowship applicants. There was a big problem last year where NSF did not fund nearly as many of these fellowships as they usually do, their main fellowship. But I think this year they funded a bunch all of a sudden. And so the numbers started to come back up. But I don't know that I've seen any data, at least I'm not aware of it, on the demographics of those recipients.
All right, Jocelyn, thanks for the whirlwind tour of all these changes. I do want to mention that you guys write about non-US science policy changes. And we can point people to, I saw this great story by Eric Stockstead on a change in the EU law to speed up approval of gene-edited crops, which is a really interesting change. They're making a distinction between editing genes and trans genes, like adding genes from other organisms.
That's right.
The other one that I should point out is this kind of outrageous idea that there is oil deep underground that is being created by non-biotic sources, so not biological sources, but some other kind of chemical processes creating giant reservoirs of oil that we don't have access to. And Russia has started a project to try to dig for these oils. It is a very controversial idea, but they are going ahead with it. They started drilling this month.
Yep.
All right, Jazz, thanks so much for coming on today, for keeping us up to date, and for all your reporting.
You're welcome.
Jocelyn Kaiser is the editor for ScienceInsider, our policy vertical. You can find these stories and more at science.org/podcast.
No one goes to Hank's for spreadsheets. They go for a darn good pizza. Lately, though, the shop's been quiet, so Hank decides to bring back the $1 slice. He asks Copilot in Microsoft Excel to look at his sales and costs and help him see if he can afford it. Copilot shows Hank where the money's going and which little extras make the dollar slice work. Now Hank has a line out the door. Hank makes the pizza, Copilot handles the spreadsheets. Learn more at m365copilot.com/work.
Apply today for a chance to win the Science and Sci-Life Lab Prize for Young Scientists. This annual prize recognizes outstanding doctoral research in life science, including cell and molecular biology, genomics, proteomics, systems biology, ecology and environment, and molecular medicine. Apply today at science.org/prizes for a chance at the $30,000 grand prize. Submissions close July 15th, 2026. Also out on the site this week, we have a feature story in our news section by freelancer Matt Hudson on the battle over how to train bots. Is pouring more and more data into these training models enough, or as building bigger and better chatbots get harder, researchers are thinking they need to turn to systems that learn to simulate the world. In our commentary section, we have a policy forum by Wintermantle that looks at a European Commission proposal aimed to simplify food and feed safety regulations that might actually increase pesticide risks. From the journals, we have a Science Advances paper by Hayes et al. Called Records of Compass Heading for Long-Distance Ocean Migrators Show Mid-Ocean Reorientation. This is looking at the very long journeys of turtles and how they reorient to their final destination along the way using magnetic fields. Okay, back to the main show here. Next up, we have Science senior editor Michael Funk. He joins us to discuss a trio of papers on the light-detecting proteins responsible for our color vision. Back in 2000, Science published a paper on the structure of the light-detecting protein in rods called rhodopsin, which interacts with light in darker settings. But the structure of the light interacting proteins in cones, which detect the colors we see in daylight vision, hasn't really been figured out until now. This week in Science, we have 3 papers on the structure of these proteins. Senior editor for Science, Michael Funk, is here to talk about what helps the different proteins respond to different colors of light. Hi, Michael. Welcome back to the podcast.
Hi, Sarah. It's great to be back on.
What took so long? Why have we known about the light interacting protein in rods, the black and white vision, if you could think about it like that, and not that much about cones?
This kind of thing is something that every human can appreciate. We all have vision and it's a really important part of our life. So a lot of people have been working on it. And honestly, people have been working on the sort of structure and biochemistry of these systems for decades. So it's kind of crazy that it took so long to get the rod system. And I think it's just taken some further advancements in the technology and the structure determination methods to get these cone structures as well.
As you say, this is very important to everybody. And we all know rods and cones from basic school biology. And so we know the difference, but only in their function. In the way that they actually make this discrimination has been mysterious because it really depends on minute details in the protein structure where light hits the protein, like where the rubber meets the road.
Yep.
And so now we have these 3 papers that take a slightly different angle at the same question. What are some of their different contributions here?
So they all have protein structures, which are the core feature, but they're all a little bit different. One of them has all 3 structures of the 3 different cone proteins.
3 different cones because we detect 3 different types of color light.
Yeah, that's right. So there's the long wavelength, the sort of medium wavelength, and then the short wavelength. And those correspond to red, green, and blue, although they kind of correspond. It's not exact.
None of it's exact. It's right into the, can you tell these colors apart? Does everybody else see those same colors?
Yeah.
One of the really important things that was pointed out in these papers is finding out what the active conformation or the active structure looks like versus the inactive state. Why was that important to kind of separate out and to thoroughly explore?
This is probably the biggest difference between one of the papers and the other 2 is one of them is looking at the active conformation. So this is after the protein has absorbed light. And it's also bound to its downstream signaling protein that actually does the signaling downstream. So that active conformation is sort of actively transmitting signal. Whereas the two papers that report on the dark state of the protein, you might think it's not active, it's less exciting, but actually those are kind of the important state to understand how these proteins are tuning the absorption spectrum. Because in the dark state, that's when you're going to be receiving the light. Whereas in the active state, they all kind of look a little similar.
Right. So they're all like in the staging, they got their mitts open and they're ready for the thing that they're supposed to be waiting for. But then once they're transmitting, they're saying the same thing: light, 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 light.
Yeah, yeah.
And so this is maybe less difference.
There are differences there too, but having that dark state is really important to understand what features of the protein are actually tuning that chromophore that's absorbing the light.
Do you want to kind of walk us through the light detecting proteins, like the rods and the cones? Can you kind of walk us through where they sit in the chain of vision, like where light gets to us and then gets to the brain?
It's a very complicated system. I was going back through sort of like textbook stuff, trying to figure out, you have this crazy contraption, Rube Goldberg machine that. So we're really concerned with the very first point where these proteins that are sitting in these photoreceptor cells are absorbing light. It's really the very first step. So what you have in the very start is you have a protein. It's bound to a retinal, 11 cis retinal, which is the sort of active thing that helps it absorb the light. The whole protein retinal complex, that is the pigment, because the protein actually does that tuning. The retinal is sort of the same across all of the proteins. So you need the whole thing to get the exact tuned spectrum of the pigment. So when you actually absorb the light, that retinal is going to change conformation. It's going to turn from a cis, which is two things on the same side of the bond, to a trans, which is one thing up, one thing down. And that conformational change within the retinal is then going to propagate to other parts of the protein that are involved in transmitting that signal downstream.
And then you get your whole cascade inside the cell. Eventually, it gets turned into electric signals.
It's a very, very, very long path to actually getting to your brain and telling your brain that something's happening outside.
The reason they wanted protein structures here, the reason why we say now that we understand what's going on is because you can look at the genetic sequence for these different opsins. So, like the protein here, and say, oh, well, they are different. So, we know that they're doing something that makes them sensitive to the wavelength of light. But actually, kind of mapping it out in three-dimensional space is what tells you how that works. Can you go into a little bit what we know about those differences now?
The genetics have been worked out for a long time, and people have even shown long before that you can change one opsin from being like a red to a green just by making a few small changes. But actually, sort of seeing that in 3D and then being able to do computational analysis combined with spectroscopy, you can really put together what's going on with the sort of electronics and the chemistry around that chromophore that's causing it to shift in where it absorbs.
Was there anything surprising in the way that these molecules are able to make these discriminations where people like, oh, yeah, of course, that's how they know what the wavelength of this particular light is?
Yeah, I'll say sort of across the three papers, it's interesting to sort of think about how these different opsins are different. The red and green are actually extremely similar. They're 95% similar. And that was surprising to me because usually when something's 95% similar, it's really similar. But there are these very subtle changes within that pocket that's binding the chromophore. And that's actually what gives you the change in color. And there's three key residues that people have known about for a while that are involved in making that shift. And you change kind of the chemistry of the amino acids that are around the chromophore, and that shifts it from red to green. Whereas if you look at the blue protein, that's actually much more different. It's only about 40% identical to the red and green. That's sort of reflected in some differences in how the protein functions sort of downstream. There's a lot of sort of subtle differences, but they also find some big changes around the chromophore. You have a different coordination environment, and that is what causes that really big shift from green all the way down to blue.
You talked about the red green being really similar. Does that relate to like red green color blindness?
So I didn't know this, but a lot of the red-green color blindness comes from sort of hybridization between those genes because they're so similar. So there are some sort of point mutations that will cause color vision deficiency. I think because they're so similar, you get other sort of effects within the genome that cause that.
Okay, really interesting.
I think so. I don't know. I'm not a
I think
geneticist,
so.
so.
I like the eyeball stuff. I'd be really interested to see how this plays out when you look at closely and distantly related animals and their cones. If they have color vision, how different are their structures? And, we're always wanting to know what it's like to see as a different animal. And this is going to help us understand that.
Yeah, for sure. Yeah, and it's a good point because this is kind of focused on the human system. A couple of these structures are from other primates that are very close to humans, but there really is a huge diversity of opsin sequences within animals. Probably very different types of vision depending on sort of what your environment is, what you need to see. Some of the evolutionary pathways that these opsins have taken are really interesting because most mammals used to be nocturnal, and humans and some other primates sort of made the transition to being more active in the day, and that came with a need for better daytime vision.
Right. So that's one thing we really need to be able to do is refresh our eyes a lot because you're constantly bombarded with light, things are moving fast, and you need to reset and make them available for the next frame of your vision. And that it's very different than at night.
That's a great point. Yeah, it's one of the things about these papers that I was excited to sort of learn more about was the differences in daytime vision versus nighttime vision. It's not just color. Color is the thing most people think of when they think of cones, but it's actually the visual acuity and the temporal resolution that these systems provide. And the proteins, when you look at them, they're very different from rhodopsin, which is the nighttime or the rod protein. How they function and how they're sort of reset is very different from that protein.
I already told you what I'm excited to learn about next, which is like how this compares to other animals and how they see the world. What do you think is going to come out of this? What are the next kind of steps for this field now that these structures have kind of been better understood?
I think having access to all this knowledge is going to help us understand, like you were saying, how animals see, but also how people see. I mean, there's lots of variation even within humans. There are color vision deficiencies that people care a lot about understanding those and maybe correcting them down the road someday. For me, fundamentally, this is just really interesting basic science. I mean, we know a lot about the visual system, and being able to see it at molecular level opens up the door to understanding the chemistry involved. And there's all kinds of other photoproteins, and sort of understanding how biological material interacts with light is, I think, a really interesting frontier for biology and chemistry.
Absolutely. And of course, I want to see how the cephalopods are doing it,
Yeah, yeah, of course.
both at the skin level and also at the eye level.
There's so many animals that have eyes that are very different from human eyes, and we're at the frontier of understanding how the systems are different at a molecular level as well.
Absolutely. All right, Michael, thanks so much for talking with me. This has just been really wonderful.
Thanks, Sarah.
Michael Funk is a senior editor for Science. You can find a link to the 3 papers we discussed at science.org/podcast. Stay tuned for the second in our 6-part series on scientific biographies. This month, host Angela Saini talks with science writer Georgina Ferry about her biography of Dorothy Hodgkin.
Hi there, I'm Angela Saini. Every month I'm interviewing the author of a scientific biography. We're up to the second book in our list by Georgina Ferry, a science writer based in England who blazed a trail for biographies about women scientists with her 1998 book about the Nobel Prize-winning crystallographer Dorothy Crowfoot Hodgkin. Ferry was motivated to write it when she realized after Hodgkin's death in 1994 that nobody else had written a book about her, even though she was such a towering figure in British science, especially famous for her work on the structures of penicillin, vitamin B12, and insulin. Georgina, you've written very many books, but this was your very first one. Can you tell me more about how you came to write it?
I was working as a science journalist and I live in Oxford, and Oxford University like many other universities, had an alumni magazine called Oxford Today. And I was essentially its science editor. I would contribute a science article for each issue. One year I thought, we've never written about Dorothy Crowfoot Hodgkin, and yet she is the only British woman who's ever won a Nobel Prize for science. So this was at the beginning of 94. And I contacted her to ask if I could interview her, but got a message back saying she was really too frail to give an interview. But I thought I'd go ahead anyway and talk to some of her former colleagues. which I did, and I wrote the article, and I sent the magazine to her when it came out. Just after that, she died, very sadly. She had a fall at home and just never recovered. But I had a letter a few weeks later from her daughter saying that she was still alive when the article arrived. They'd read it to her and she liked it. And would I like to come and visit? This is a characteristic of the Hodgkin family, that if they can't think what to say, they invite you over. So I went to see her daughter Elizabeth and found that there was a certain amount of autobiographical material which Dorothy had written, but which really wasn't in a publishable state. And she was wondering what to do about it. And I said, well, who's doing the biography? Because I had this naive assumption that anybody of her level of distinction must have a biographer, and there wasn't one.
It is remarkable that she didn't have a biography already. Let's start at the beginning. Hodgkin was born in 1910, when it was still quite unusual for girls in England to get exactly the same kind of education that boys got. How did she become interested in science? Was it immediately clear how brilliant she was? And if it was, then who encouraged her?
Well, her parents. There's no two ways about it. Her parents were an extraordinarily equal couple for the time. Her mother had rather conventional parents, and so she hadn't been able to have a university education. But she was very self-educated and very interested in lots of things. And her father worked mainly for the British Colonial Service and was head of education for the British Colonial Administration in Egypt. And they had 4 daughters. They were given a very sort of free upbringing. The only thing they might be criticized for would be for being lazy or underoccupied. But whatever they were interested in, they were able to pursue. As you said, Dorothy was born in 1910 in Cairo. 4 years later, the First World War broke out, and the 3 girls who'd been born by that time were all sent back to the UK and barely saw their parents throughout the war. They were cared for by relatives and friends in the UK. And then after the war, her mother came back, and her schooling was pretty sketchy up to that point. But when she was 10, she went to a small school. There was something called the Parents' National Educational Union, which ran little classes, mainly in domestic properties, just in people's homes. One term was chemistry, and they had to grow crystals. And Dorothy has written numerous times, I was captured for life by chemistry and by crystals, just because they were so beautiful. She went to the local state school in Beccles, which was near her home, in their home in Norfolk, where the chemistry teacher was a woman. Pretty unusual. But even though that was the case, it was a mixed school, but girls weren't supposed to do chemistry, they were supposed to do needlework. But because Dorothy had already got this passion for chemistry, she fought to be allowed to study chemistry, and she and one other girl were able to study chemistry. And yes, she did extremely well at school. Her father felt that she should be educated in the same way as if she'd been a boy. He'd been to Oxford University. He thought she should go to Oxford University. And there were certain gaps in her education, so she had to spend an extra year mugging up on extra science and maths in order to get her place. But she got a place at Somerville College in 1928, when she was only 18. I mean, if she'd gone the year before, she would have been very, very young.
So as you say, she was drawn to crystals from a very young age. And at one point you write in the book that she never could resist a well-formed crystal. That passion persisted when she went on to study crystallography. Why did this happen to be a promising avenue for a scientist like her to be pursuing at that time?
Well, I think her timing was extremely fortunate. It was a completely new technique in the biological sciences. So it was pretty new all round. It had been discovered in 1913, 1914 as a way of seeing the arrangement of atoms in crystals by using X-rays, passing X-rays through the crystal and catching the pattern of diffracted spots that you would get on photographic film. But after she graduated and she went to Cambridge to do her PhD, there she found her supervisor was a chap called J.D. Bernal, who was among the first to be using this technique. Look at the kind of molecules that we have in our cells, that the important molecules that drive all the functions of a living body. And so she was in right on the very ground floor. And one category of these molecules is proteins. Proteins do nearly all the hard work in the body. And nobody had attempted to use crystallography to look at a protein until J.D. Bernal got crystals of pepsin in Cambridge, and Dorothy worked with him on that project. So they had a paper in Nature when she hadn't even finished her PhD, and it was the first paper ever in structural biology. There was her name right from the very start. But I think it was exciting because nobody knew what shape proteins, but nobody knew how proteins worked.
It was a very exciting area of science, and she was clearly devoted to it. That's very clear in your book. But there was so much more to her. She had a fascinating personal life, and you've already mentioned that one of her colleagues was J.D. Bernal at Cambridge, who she fell in love with before she met her husband. What did you learn about that relationship with Bernal?
Bernal was very left-wing. Most of the people around him had similar left-wing beliefs. And what seemed to go along with that in the early 30s was a belief in free love. So the conventions of marriage were often regarded as not applying necessarily. And Bernal had infinite numbers of affairs. He was married. He had 2 other very long-term relationships, but he had relationships with loads of other people. And for a long time, it was thought that Dorothy was the exception that proved the rule. And she was very beautiful and very young when she was working with him. And the fact that they had a relationship was kept very, very quiet. But when I was writing the book, I first of all didn't mention the fact that they'd had an affair. And it was her daughter, Elizabeth, who said, "Why didn't you put that in?" And so I went back and put it in. But yes, I think he was pushing for a physical relationship. She wasn't so interested. She adored him, but I think she regarded him as he was known as Sage. It was his nickname. And to her, he was the sage. He was the fount of all knowledge. She absolutely accepted all his political beliefs and she admired him. He was a magnetic character. But I think she felt that it wasn't a relationship that had a future. She came from a very close, loving family with 2 parents who adored each other. And I think she saw that as the ideal for herself.
I also want to go back to politics because, as you say, Bernal was very political. She was very interested in politics herself and supported political causes, which is perhaps unsurprising because she did live through 2 world wars. So this was, part of living in the 20th century. Can you explain more about that side of her?
Well, again, it went back to her childhood. I mean, her mother was a Labour Party supporter in the teens of the 20th century. There's a story that Dorothy herself stood for election as a Labour member at a school mock election and polled 2 or 3 votes in the whole school. But she was brave enough to stand up and make a pitch for Labour. Her mother also was a tremendous internationalist and actually took Dorothy to see a meeting of the League of Nations when Dorothy was only 14. And so she had a great sense of the countries of the world being able to sit down and have a dialogue about resolving problems rather than conflict. I think that was fundamental to her politics. So she wasn't somebody who necessarily wanted to wear a badge or shout slogans, but her instincts were all very much on the progressive left. She was a member of the Labour Party. Her husband Thomas was a communist, as was Bernal, but I never found, and she had lots of friends who were communists, and she had no reason not to like communists, and she spent a lot of time in both Russia and China later on. But as far as I can find out, and I did look at all her papers and she never threw anything away, she never actually joined the party herself. And there is one letter to her husband where she says, "I stayed up all night wondering whether or not to join the party, a decision that was eventually shelved."
It is interesting reading biographies of scientists who lived through the 20th century. It's almost like reading about world history because so much happened politically and socially in those decades. Hodgkin personally knew many of these famous people, lived through so many significant events. But one that stood out for me in your book was that among her students, very briefly, was Margaret Thatcher, who, of course, then became Britain's Prime Minister much later. What was that like for both of them? Did they ever reflect on the significance of them both being female pioneers in their respective areas?
Margaret Thatcher has been interviewed about Dorothy. Dorothy has been asked 1 or 2 questions about Margaret Thatcher. The situation was that Dorothy, from early or even before the war, was the science fellow at Somerville College, Women's College at Oxford. And Margaret Roberts, as she then was, studied chemistry at Somerville. So Dorothy would have been supervising her work all the way through the first 3 years of her degree. And then the way chemistry still is taught at Oxford is you have to do a 4th year of research. And Margaret Roberts chose to do her 4th year of research in Dorothy Hodgkin's lab. So she worked on a form of antibiotic in Dorothy's lab for a year. I would say that Dorothy, when she was asked about Margaret Thatcher, gave the impression that she thought she made a better politician than a chemist. Although she did. I mean, her first job, she went to work for Lions in their ice cream division. as a food technologist. So she did have the beginnings of a scientific career, an applied science career, but very quickly moved into law and politics. As for Margaret Thatcher, it's very interesting because, I did interview her myself. Their political positions could not be further apart, but she never stopped admiring Dorothy. She admired her tremendously, and it was very helpful to Dorothy because whenever she had an issue she wanted to pursue, such as détente with Russia, these big global issues, she pretty much had an open door. She lunched at Chequers with Margaret Thatcher on a number of occasions. If she wrote to Margaret Thatcher or one of the other ministers at the time, she could be guaranteed the letter would be seriously considered. Whether they actually took any of her advice is another question, but she was certainly always received with courtesy. And the one thing that Margaret Thatcher emphasized when I spoke to her was that she admired her completely. And there's a story told by some Russian crystallographers who came on a Royal Society visit to London and were taken for an audience with Margaret Thatcher in her office at number 10. And there on the wall behind her was a portrait of Dorothy Hodgkin, who they all knew personally and were very impressed to see her portrait on the wall.
That's amazing. I wanted to ask you finally just about your writing process. There is a huge amount of detail, beautiful detail in your book. It almost feels as though Dorothy Hodgkin wrote it herself because her voice is so vivid throughout. What were your sources and how close do you think you came to capturing her as she really was?
I hope I came pretty close. She's elusive. She is elusive in some ways. But as you say, it's the voice, and that obviously comes from the personal letters. She had a somewhat unorthodox marriage. Her husband was not entirely faithful, but also he had a busy professional life of his own that often took him away, for long periods of time. And whenever they were apart, they wrote to each other almost every day. And he wasn't a scientist, he was a historian. So obviously, if she was writing to him about her work, she wouldn't be writing in a very detailed way. She'd be writing about how she felt about it, how it was going, all the things that you don't get from the published record or from correspondence with other colleagues. And the family were just wonderful at letting me have complete access to this wonderful archive of personal letters. And I think that's really the secret of the sense of her as an individual that I hope comes out of my pages.
Yeah, it really does. So very last question. Your original biography came out in 1998, I think. And actually, I was about to go to university then. I was going to Oxford myself to study engineering. And I remember one of the governors at my school gave me the book to inspire me to feel that you're a woman becoming an engineer and here is another woman scientist of the 20th century who did great things.
That's lovely to hear.
And this is one reason why I was so keen to interview you. The book that I was sent by your publishers is the updated edition, which was reissued 20 years later. And I did wonder, what did you add to that was new? What did you add in those intervening years?
Not very much. I was delighted that they were prepared to reissue it because it had gone out of print earlier. I think I changed one image. Obviously, things like if people I mentioned as being alive had died, I made it clear that they had died. One thing that happened was that a set of circumstances, which I won't go into, I never managed to find much, if any, correspondence between her and Bernal. And I thought there must be some. I know she never threw anything away. She must have letters from Bernal. And quite a long time after the original edition was published, while looking for something else, I discovered that those letters had all been filed with Thomas Hodgkin's correspondence, which weren't properly catalogued. They were all just in big cardboard boxes. But with help from Elizabeth Hodgkin, I was able to fish out some of those letters so I could flesh out the relationship between her and Bernal a little more with some of his voice as well as her own. Other than that, I didn't do a big rewrite.
Well, it's a lovely book. Georgina Ferry, thank you so much.
Not at all. It's been a pleasure.
Next month, I'll be interviewing zoologist Matthew Cobb about his new biography of another Nobel Prize winner, Francis Crick. See you then.
And that concludes this edition of the Science Podcast. If you have any comments or suggestions, write to us at sciencepodcast@aaas.org. You can comment on Spotify too, or YouTube, where we now host the podcast as well. To find us on those apps, search for Science Magazine, or you can listen on our website, science.org/podcast. This show was edited by me, Sarah Crespi, and Kevin McLean. We had production help from Podigy. Our music is by Jeffrey Cook and Wenkoi Wen. On behalf of Science and its publisher, AAAS, thanks for joining us.